All right, with that though, let's turn that out of the way for the moment and take a quick look back at, wrong keyboard on the computer, here we go. There we are. Take a quick look back at where we left off last week. So last week, we talked about vector subspaces. So we have our familiar sets, the reals, real vectors, C infinity. And then we said those are all vector spaces under our usual adding and scalar multiplication rules. Then we said, all right, so we can look at subsets of those because subsets of those might be interesting. And especially for functions, if we're looking at subsets that might include solutions to differential equations, that's going to be a rich source of vector subspaces. And we learned about the 3 rules for that. We just had to show if we're working with a known big vector space and we're just worried about this little subset, and you've already had this in your web work as well, examples of this, what makes a subset still a vector space? How can we guarantee that the rules still work in that subspace? And it's that 0 vector closed under addition and closed under scalar multiplication checks. And then we narrowed down even further and said, well, what if I just have some building blocks? What if I just have some vectors? I'm trying to get myself on the screen here. A few vectors. Can I build from those? And from those, I can build subspaces. And what kind of subspaces are those? And we're going to be focusing really on those vectors this week, properties of them, and seeing, you know, do we have redundant sets? Anyway, we'll see it as it plays out. But just a quick reminder about this idea of building block vectors. So these are like building blocks. And then we have the span of those, which is any linear combination. Combination of the building blocks. All right. And again, a linear combination is a very specific combination, but it's a very intuitive one. It's, okay, I've got vector 1, I'm allowed to scale it. And I have vector 2, I'm allowed to scale it by some real number, and I can combine those by adding in any way I like. So some of these values could be 0. So you can actually say that V1 is in the span of this set because I could have 1 V1 and 0 everything else. So it's not just those vectors. I can recreate those vectors, and then I can also create these other elements with it. And that really does beg for a picture. So, yeah. So if we had vector like V1 here, and this is in R3, if we had V1, V2, and V3 pointing off in all different directions, then the span of R3, the span of those 3 vectors would be all of R3, span of V1, V2, V3, because we can get to any point through some combination of those 3 vectors. Let me try to get this a bit better here. Something like that. So I could have some V1s, A1, V1, A2, V2, A3, V3, and some amount of V2. And if we add those head to tail, going in this direction, going parallel to V2, well, this is V2, sorry. I apologize for that. This is A2, V2, and A3, V3. Pete's sake. Oh, it's hard to get fine-tuned erasing here. V3. There we go. So we can follow V1 for a while, that's that direction. And then we can follow V2 for a while. And again, the how much time or how long a vector is defined by that scaling factor. And then we can go back on V3. I know my diagram's not that great. Let me tweak it a little bit. Go further in like that. There's V3. And the idea is that we can reach any point. So we often think about these building blocks and you think about getting out to all the points. And the question that just came up in the chat is, how do we know whether we can get to all the points? That's in fact the biggest question we're going to face today. We're going to be looking at vectors and seeing what's the process we're going to go through to determine whether we can reach individual other vectors or all possible vectors and see what the conditions are for that. So let's take this on a micro scale. So these are in R4. It's R4. And I have 2 vectors here. And I'm asking whether this vector here is in the span of the first 2. So think about that for a second, and I'm just going to flip over to our clicker questions here. Next question. There we go. So first off, translating this into words, what does it mean to be in the span of? What does it mean that W, this individual vector, is in the span of V1 and V2? That's the first clicker question. Excellent. I'm good on that one, so I won't belabor that. Strong preference there for C, which is exactly right. W is a linear combination of those two. So we're asking the question, is W a linear combination of V1, V2? So I'm picking different styles here, V1, V2. That's an equivalent question. All right, now follow up. Going to the next clicker question here for a second. There we go. Is this obvious? Like if I'm looking at this page, is this the kind of thing that, oh yeah, I just look at it and go, yes, it is? Or does it take more work? Like, is it going to be a process? Is it going to be obvious, or is it going to be a process? Interesting. Okay, I like the optimism of some of you here. So I'm actually curious if the people who are saying it's obvious. If you had me in 171, you know the follow-up question in class would be, okay, if it's obvious, tell me, is W in the span of V1, V2? It's a little more problematic online, but if anyone wants to throw in who said obvious, how is it obvious, and is the answer yes or no? Either in the chat or unmuting. Don't you know it's included? Good point. So the vectors here aren't parallel. That's true. But the problem is they're only going to make a plane. So let's actually model this as if it's R3 for a second. So we have V1 and we have V2. But because we're in a higher dimension than just 2, what that's going to define in terms of the span is going to be, we call it a hyperplane. The span of V1, V2. But because we have 4 dimensions to play with, and these 2 vectors can only ever cover a plane of it, 2 dimensions of it, and we're going to define dimensions in the next few weeks, then we actually have 2 options still. We could have this span, try to draw it the same way both places. Our W could either be in the plane. That's, again, it's I don't want to get into details, but it's a hyperplane just because we're not in 3D, we're in 4D. Or W could be pointing off of this. This would be our analogy. W not in the hyperplane here. So because we have a lot of dimensions to play with, it's very possible that it's not in there. Okay, now I think Cambridge has got the bang on answer here, is that it's not obvious unless you dive into some of the calculations. And that's what we really have to do here. So I would say obvious, generally speaking, no. If you want to say not usually. The span question really, in most cases, it becomes a calculational problem. You have to look at these vectors in detail, look at individual coefficients, and work out whether it is possible to make this vector out of these ones. And let's find out by actually showing how that works. So usually we need a calculation. Calculation to determine if W is an element of the span of V1, V2. All right. Then yes, Jack, you're getting ahead of where we're going, but it's absolutely true. In fact, sorry, the statement there was, does the span need to have 3 vectors in order to cover R3, 4 vectors in order to cover R4? Absolutely. And it turns out there's a little more to it than that. Just like we saw in 2 dimensions, you need to have 2 vectors to cover 2 dimensions to make a big, to be able to have the span cover all of R2. But you also need something more than that, because you don't want to have 2 vectors that are parallel to each other. And that's kind of what we're heading towards today, is when do we have sort of unique, or the span of these vectors is unique, that kind of thing. We're going to talk about a concept called linear independence and dependence in a second. But absolutely, to get and cover 2 dimensions like R2, you're going to have at least 2 vectors. To cover R3, you need 3 vectors and so on. That actually becomes our definition, or part of the definition of dimensionality. All right, so this calculation, what does the linear combination look like? To be in the span, we're asking, does A times 1, 0, -2, 1 plus B -1, 1, 3, -2 equal 2, 1, -3, 0 have a solution with A and B being real numbers? Question mark. Oops. Question mark. We want to know if W is in the span. Well, W is in the span if I can make a linear combination of V1, V2. Here's V1, here's V2. If I can make a linear combination of them, so some arbitrary constants out front, if I can find a solution to this, then I'm good. If I can't find a solution, then I can't. And there was that earlier idea that some of these coefficients are not going to work out, but let's see that in calculation form. So let's look at components. A times 1 plus B times -1 has to equal 2. The second component has 0A, so I'll just leave that off and have B equal 1. Third component is A times -2 and B times 3 has to equal -3. And the last component is A times 1 plus B times -2 has to equal 0. So right away, we get one of these equations. Let's call that equation 2. And we can really sub it wherever we want. Let's sub it into here. Sub it into equation 1. If we do that, we get A plus B is 1, yes. B is 1 times -1 equals 2. And that gives us A equals 2 plus 1, which is 3. Now, that's great. We've got an A value, but does it work for all the equations? So we're going to check it. Check whether A equals 3, B equals 1 works for equation 3 and 4. Give those some numbers here. And let's go into 3. Oh, how do we know B equals 1? B equals 1 comes out of looking at the second coefficients across all of these. So we had A times 0, which made our lives a little bit easier, and B times 1. So 0 A's plus B times 1 equals 1 was our shortcut for that. We got nice coefficients that helped us do that a little more quickly. So yeah, the left-hand side here, because we're checking, is A we said would be 3 times -2. So I'm just using these values here and checking to see what the left-hand side equals. And B was 1 times 3. And so that's -6 plus 3, that's -3. Oh, so that's good. I'm doing a calculation here, that looks good. All right, and 4 tells us from the left-hand side, sorry, that equals the right-hand side. And 4, the left-hand side is 3 plus 1 times -2. And that is, oh, that's 1. And that is not equal to the 0, which is the right-hand side. Oh, we're so close. And so this solution doesn't work, arg. and there's no other option. As soon as we have this equation, B had to equal 1. As soon as we match that with the first equation, A had to be 3. And it worked for the third equation, but it doesn't work for the fourth, and there's no other way to make it work. That means that there's no solution AB that satisfies all equations. That satisfies all equations. And that means that W is not a linear combination of V1, V2. And that means not in the span. Not in the span. I really could use my space better. Span of V1, V2. These two statements here, being a linear combination of or being in the span, those mean the same thing. So if we show that W cannot be made a linear combination of V1, V2, then W here is not in the span of those two things. And so here, the no solution is solving for the coefficients in the linear combination. So we set up a generic linear combination, and then we ask, is there a solution to this? Can I make this equation true by picking the right values for A and B? We did a whole pile of work and said, no, we can't. I've found some values for A and B, but they don't work for all 4 equations. So that means there's no single value of A and B that'll work for all 4 equations. And that means this equation cannot be solved. There is no solution for A and B that makes this equation true. And so it's not in the span. And so it's not a linear, W is not a linear combination. And so what we have is this kind of scenario here. We've got our plane, hyperplane. We've got these two vectors, V1, V2, that are defining a span. And just so happens that W is in some other direction than them, or their combined span. And that's just the way it is. It's not no judgment here. It's just where W lies with respect to W1 or V1, V2. Could you have this with addition and scalar multiplication redefined? Absolutely. I mean, this is all contingent on, here we set R4. So we have to define the space that we're working in. We're in R4, and unless we specify otherwise, it's the usual vector addition. How do we add vectors? And scalar multiplication, we relied on that throughout that calculation. When we get to this part of the course, we don't typically mess around with the weird spaces as much for linear independence, as we're going to see. It just gets a little too counterintuitive. We just want to have it on your radar that it's possible to have weird vector spaces, but generally speaking, when we get to these calculational exercises, we try to keep it more straightforward for you. All right, let's try the same idea again, but not too surprisingly, it'll work out this time. Notice that I got this wrong for one thing. This is R3. And we had the same question. I've got this vector here, and now we are in R3. And my question is, well, can I add up combinations of these two vectors to get this? I.e., so it's the vector in the span of V1, V2. An alternative way to ask that question is there a solution, A, B, element of the reals, such that A times -2, -1, 1, plus B times 1, 2, -1 equals our target vector here, this W, 0, 12, -4. That's our V1. That's our V2. This whole thing is a linear combination of V1, V2. And there's a W. All right. Again, so I would say, is this obvious? Not to me. I mean, I'm looking at it going, maybe, but when I say, if it turns out to be obvious, it's because I'm carefully looking at each component and doing some math in my head. So it's not, you just look at it and know. It's either you do calculations on paper or you're doing calculations on in your head. So specifically, we're going to work with components again to get our equations, because that's how we know how to solve equations. If I have A times -2, B times 1 equals 0. That's the first component. So I'm going to have A times -2 plus B times 1 equals 0. If I take the second component, I'm going to B times 2 equals 12. and a times 1 plus b times -1 equals -4. And so we had those three equations. Let's number them again, 1, 2, and 3. This time we don't have any nice zeros on the left-hand side, unfortunately. We're kind of stuck with 3 equations, 2 unknowns. So let's take 1, which leads us to b equals, I bring the -2a to the other side, I get 2a. And then let's call that 4. Doesn't really matter. Let's put it into 2 here. 4 into 2. And you can solve these any way you like. This is classic. I've got a bunch of equations. They're all linear, fortunately. So it doesn't matter how you solve them in terms of order or process, as long as you're using the rules and operations of manipulating equations. 4 into 2 here gives us -a plus 2b's, which is 4a's. Let's do it in detail here. It's 2 times 2a, because this part in here is what b is. And that equals 12. And so that gives us 4a minus a, that's 3a, equals 12, or a equals 4. And that immediately tells us that through equation 4 here, that b, which is equal to 2a, is equal to 8. Handwriting, 2a. There we are. And are we done yet? Of course not, we're not done yet, because we've only used the first 2 equations. What we have so far satisfies them, but does it satisfy equation 3? We just need to check that. The left-hand side of number 3 is a, and a is 4. So 4 plus -1 times b, b was 8. And that is equal to 4 minus 8, that is -4. That does equal the right-hand side, check mark. So a equals 4. Actually, I think I have space on the next page. We're gonna do the next page. So we found a solution, and it seems to work for all 3 equations. And so we found that 4, which is our a value, times -2, -1, 1. Is that right? Yeah, okay. So I thought maybe I got it backwards. Plus 8, which is our b value, times 1 to -1 equals 0, 12, -4. And just a quick sanity check, -8 plus 8 is 0. -4 plus 16 is 12, and 4 minus 8 is -4. Yeah, good check. So it's obvious now that W is in fact a linear combination of V1 and V2, but only because we did a reasonable amount of calculational work to get there. So W is a linear combination of V1, V2, V1, V2, and that means W is in the span of V1, V2. And again, just comparing and contrasting the scenarios here. Let's go from this way. If we have our V1, V2 that are defining, this is actually an R3, so it kind of defines a plane. Then W somehow is inside that plane. It's something I can build using V1, V2, which can reach any point in the plane. W is one of the members of that plane. And again, we are in R3 here, so we could, oops, no, we can't do that. We have to base ourselves at the same point. The origin has to be in there as our base point for all these things. All right. Let me just pause there for a second while folks are catching up on writing. So what we're trying to build in terms of intuition here is this idea of, are you in, is a vector in or out of the span of some other ones? That we're trying to think about directionality. We're going to see it in function spaces in our next example, but also recognizing that the test for these things is often very computational. It's often I need to write up a bunch of equations and solve them. And if there is a solution, then that means one thing. If there's no solution, that means something else. All right. The span is a plane, because it consists of two vectors, and again, there's this extra caveat, and they're not parallel to each other. Yes, exactly. All right, so just to show that this is not just about vectors, but the language of vectors can be extended to here, C infinity. So the question, we'd phrase it one of two ways here, depending on whether we're feeling like linear algebra is our umbrella or whether we're thinking more calculus-y. But we could say, is the function W here in the span of the two functions V1 and V2? If we're talking linear algebra, we could also say, is the vector, because it's an element of some set in this language we're using for linear algebra, is the vector W in the span of the vector V1, V2? We would just, on a day-to-day basis, call these things functions because that's what they kind of look like. Well, how do we do this? Well, it's the same thing. We're asking, is there a solution? A, B, element of the reals, and I'm always picking A and B because I only have two input vectors or functions here. Is there a solution A, B, element of reals for A V1 plus B V2 equals W? It's exactly the same condition. And now we're just going to look at it to see whether that makes what the math looks like here. And the beautiful thing about this is because we're dealing with polynomials, we know implicitly, we're going to focus on this more a bit later on, but we know implicitly already that I can't add constants and get x squared functions. Like constant functions do one thing, linear functions do one thing, quadratics do another thing. Those are all distinct operations. And so we can think of it almost like this. A times, we've got 3 plus 0x. I'm just going to put these brackets around here. I'm just going to line these things up, sort of looking like a vector because there's a lot of analogies between them, plus 0x cubed, plus b times 0 minus 2 x's. So I'm just going constant x squared, x cubed, minus 2x plus x squared plus x cubed equals 3 plus 2x, 0x squareds minus an x cubed. So these stacks here, I mean, I wrote them vertically. You don't have to. I could have written them out longhand, horizontally, but they're just a restatement of these three functions here. So there's been no transformation that happened here. However, I think if you write it vertically and go back to what we did here, it becomes more obvious that, oh, what am I setting up? I'm setting up a bunch of equations. And what has to be true? Well, I have to have the constant terms equal to each other. So I have to have A times 3 plus B times 0 equal 3. And that's separate from any calculations related to the x squared, and x cubes. So instead of components here, though I'll write it as components for the parallel, what we end up with are coefficient equations, coefficient equalities. What makes these three cubics, they're all implicitly cubics, just some of them with 0x cubes. What makes these cubics the same? It's the fact that they have the same coefficient for all the different terms. So we have A times 3 plus B times 0 has to add up to 3. And A times 0 plus B times -2 has to add up to 2. Now notice what I'm kind of leaving out here. I'm leaving out the x's. I just want the coefficients of them. This is the x equation. This is the constant equation. And then I have the x squareds and the x cubes. So just going down the list, we have A times 1 and B times 1 equals 0. And A times 0 plus B times 1 equals -1. And so someone's actually ahead of the game. I saw in the chat there. That's Nigel. Thank you for that. You can quickly check some of these and go, oh, this is b equals -1. That has to be the answer because the a0 doesn't appear. Up here, this equation quickly gets us that a has to equal +1. Let's make it clear it's +1. And then I can check both of these. And if I sub in 1 times 1 plus -1 times 1, that equals 0, check. And b times -2 is 2. That is true because -1 times -2 equals 2, check. So this does have a solution. We can take one of the first functions, -1 of the second function, and we'll get our w. So I'll just put that onto the next page for clarity, but I'll give folks a second to catch up with any copying you're doing. Move to the next page. We found that 1 times 3 plus x squared plus -1 times -2x plus x squared plus x cubed equals 3 plus 2x minus x cubed. And so our ingredients here were A, V1, B, V2, and W. And again, never hurts to do a quick sanity check. I have +3, +3. X's, no X's. I have +2X's, +2X's. Perfect. X squareds, I have +x squared minus x squared. Oh, 0x squareds. And x cubes, I should have -x cubed. I have -x cubed. Yep, that's perfect. So W is a linear combination of V1, V2. And that means that W is in the span of V1, V2. I can reach V1, V2 with, reach W with V1, V2, but reaching here has a very different feeling. It's more like I can build this function out of these building blocks. Here, the building block concept or image, I think, is more helpful than thinking about directionality. What I would emphasize, though, is that there's parallels here that are not obvious on the surface until you kind of write it out, especially when you write it out in this kind of way. The math here looks almost identical to the math with vectors, only instead of talking about an x, y, z, and w components, we're talking about constant x, x squared, x cubed. So there's some really close parallels between how we talk about adding, subtracting, scaling polynomials and adding, subtracting, and scaling Rn vectors. So something to keep an eye on. All right. So what, this is going to make, you thought things were circular before. Here we're going to have even more circularity. So last week, we looked at the end of the week and said, hey, when I'm looking at a linear system of equations, we can transform that. Sorry, and the question was, does it have a solution? Does it have a solution? And actually, we can be more specific. Does it have 0, 1, or infinite number of solutions? That's really what we want to tease out. Linear equations have those three options. And when we look at this, again, it's not obvious. But what we were able to do is say, oh, wait, I can reframe this a little bit. If I notice the coefficients are 1, 2, and 4, 1, 2, and 4, and then 3, 1, minus 1, 3, 1, minus 1, I can expand this to say, this question, does this have solutions, is the same as saying, is this vector here, this in the span of, let's call it V1, V2 here, V1, V2, if we give those labels. So here we were given a set of linear equations and we invented some vectors. We constructed some vectors. We constructed two vectors, and it turns out that if we construct them by using the coefficients of x1 and x2 here, we get a vector form. And we're like, oh, well, that is a linear combination. This is something that's on the right-hand side. It's in the span or it's not in the span of the two building blocks. What we just did today was we went backwards. We said, hey, if I have a vector and I want to know if it's in the span of these vectors, I end up building a system of equations and I try to solve it. So this is a very common theme in engineering math where you have this duality. And sometimes it's helpful to look at one side or the other, but we often do go back and forth either explicitly or implicitly all the time. So when we're looking at the question, is this vector in the span of these things here? The way we answer that question, at least one way to answer that question, is to build a corresponding set of equations and try to solve it using our regular solving techniques. So keep that in mind. We're going to have both of these forms, system of equations, or something in the span of something else, a set of vectors, and we're going to play with that a little bit. Okay, now here we're getting to the question people were hinting at with a span. And again, this is kind of like, yeah, let's do the R2 version first. I think it's more clear. So if you pick V1 and V2, doesn't actually make it even like that, V2 versus V1, turn these straight lines, V1, and let's make it longer, but V2 here. I think you can see just looking at this that the span here of V1, V2 is all of R2, whereas here the span of V1, V2 is not all of R2. It's just points on the line parallel to V1, V2, V1 or V2, and or really because they're both parallel to the same line, and or V2. And what we could do here is we could set up an equation that A times V1 plus B times V2. So the proof for this proof would be solving equals XY for any XY in R2. We were dealing with individual points before, but in principle, you can just imagine any point somewhere on the plane. Let's go over here somewhere like some XY. Can I make this point out of following V1 and then following V2? Oh, that would be setting up a system of equations, some multiple of V1, some multiple of V2 equals any XY I care to mention. Okay, so sorry, linear independence. This is the title of this section. We're going to define it in a second. What ruins most students' day about this part of the course is that in 2D, this distinction between if I have two vectors, as long as they're not parallel, I can get to everywhere in R2. Most people get that. That's not a problem. If as soon as I have two parallel vectors, then, oh, well, then I can't get off that line somehow. They're both in the same direction. And so, this is the next slide. Yeah. So there's a difference between those two vector sets. The linear independence and dependence are they're going to be labels that we stick on those two cases. The problem is it's not as simple as parallel and not parallel when we have higher dimensions, as I'm going to show you in a second. So these things are going to be like, I can actually put it here. Linear independence is going to describe this case. Linear dependence is going to describe this case. So you can think of linear dependence as sort of a meta parallel, but I think it'll be easier if I see it in 3D. So in 3D, if we have three vectors, so let's pick three vectors like so, V1, I won't pick them on the axes just to make it different there, but somehow fundamentally pointing in different directions. And again, it's hard to see this in 3D, but that'd be the idea. So V1, V2, V3. The span of V1, V2, V3 is all of R3. And just, again, using intuition for now, stick your fingers up in the air, as long as they're pointing in some different directions, like your physics right-hand rule kind of stuff. Anytime you make one of those kinds of sets of vectors, you can feel, yeah, I can go out in X, I can go up in Z, maybe not X, Y, and Z, I can rotate it, but I can get anywhere because they're pointing in different directions. However, that's not always the case. If I imagine two vectors, v1, v2, that are not parallel, that's fine. v2. But what if what if those define a plane? And then my third vector, v3, is also in that plane. So v1, v2, v3 are all within a plane together. That would tell us the span of v1, v2, v3 is not all of R3. Okay. And you can imagine that very easily, right? You take your three vectors in your hand, all of a sudden, if you just put them so they're collinear, so they're flat, trying to get some of the camera there. If they're all flat together, well, then I can't ever leave that plane. There's no, I can't get into that third dimension, even if I twist on my side. There's some other dimension that I can't reach. And this has got parallels to what you're imagining when you're looking at the tangent planes and so on in calculus right now, 172. They would, yes, they would span the entire plane that they are able to reach. So there's a span. This plane here would be the span of v1, 2, 3. All right, but it's not all of the three dimensions. So here we're trying to tackle the idea of when is there something redundant somehow or not. In this case here, in some sense, if I've got my three vectors, they're all going in different directions somehow. I can't remove any of them. I can't take one of these vectors away and still reach all of R3. Whereas here, I could take out v1 and I could just talk about the span of v2 and v3 and go, it's the same thing, right? This v1's in the plane, but v2 and v3 are enough by themselves to define that plane, so I can throw away v1. But it's not even that nice. I could actually throw away v2 and keep v1 and v3. Or so it's not guaranteed that it's not like one of them is redundant. It's that any one of them could be redundant in principle, or maybe some of them could be redundant, but only one at a time. We get into this weird kind of logic that's more complicated than parallel, not parallel. But it's capturing the same idea that applies. It's the generalization of this parallel and not parallel. Somehow there's redundancy here, just like once I already have v1, v2 is offering no new direction, no new information, no new reach if we're talking spans. Here, it's more subtle, but yeah, all three of them together, they share some kind of redundancy in that one of them could be removed without affecting the span, the places I can reach. Over here, that's not the case. So that's what we're going to try to work with and define over the next few slides. In terms of Ariel's question, I wish it was as nice as X, Y, and Z, but again, because you can rotate these things, you might have a perfectly good plane that X, Y, and Z are all changing. Like take some of the ones again from 172. It's a perfectly good plane, and you have three vectors in it, but it doesn't have to be there is a relationship between X, Y, and Z, but it won't be like, oh, X and Y are being used and Z is not. It could be some combination, and usually will be some combination of all three changing at the same time. So it tends to be non-obvious, again, whether you have this situation or this situation. Telling the difference between these two is going to involve, wait for it, solving linear systems of equations, because we're basically talking about span and vectors again. So let's get into that detail. Sorry, functions. We'll do a little stopover in functions, but we'll just wave our hands at this one here. Compare the span of the following sets of functions from C infinity. And here you can see there's a 1 function. There's a 1 plus x. And you can imagine between the two of them, if I add this and subtract that, I could also reach x functions. And I also have the 1 plus x squared. And I can imagine that if I combine these two, I can get x squared functions. If I add this and I subtract one of these. So linear combinations, I'm allowed to add and subtract multiples. So I can get ones. So the span of this, of 1 plus x, and 1 plus x squareds is going to equal all of P2, all quadratic polynomials. By taking combinations of these, I believe I can build any x squared constant function because I can see all the ingredients here. To compare and contrast over here, this is kind of like missing the z. Obviously, it's functions is hard to work with anyway, so I didn't want to make it too hard. But here we can see I've got a 1 minus x squared, and I have a 3 plus 2x squareds. Just at a glance, there's no x's here. This is like just missing the z component, like the earlier thought. Sorry, there's no x's, no x to the power 1s, to make it explicit here, in here in the set. And right away, that means we know we can't build all of the quadratics. So the span is not all of P2. Can't build, for example, 3 plus x. There's no way to build this x from, this is absent from our 1 minus x squared, 3 plus 2x squared. So even with functions, we can talk about, can I reach a certain span? Even though I have 3 functions in both of these things, somehow there's an analogy that I can't get all of P2 out of this because there's some redundancy in here. You can almost see it. I can build this guy out of these other 2, whereas these ones, I can't build this function out of the other ones in the same way. And that building idea is really how we get to our definition. So we have time. Yeah, this will be our round off, and we'll springboard and use this like crazy on our class tomorrow. So definition of linear dependent and independent. We start with a set. And this is going to feel so weird. I know it. It felt weird for me. This is just prepare yourself. Brace yourselves emotionally for something feeling weird. I'm going to take these things and I'm going to call them linearly independent. And for what we're going to use later, this is the independent case. Independent. There's all somehow, they're going their own way. They're independent. They're children of the 90s, whatever it is. That is the same thing for here. These are going to be linearly independent here. It's the 3 vectors going in different directions. So that's your analogy. Those are the ones I'm looking for. They're linearly dependent if I try to add them up. So I try to add them up, try to combine them to get 0. And this is the idea to get them to cancel out. So if I can add these things up and get them to get to 0, that means somehow they cancel each other out. Here's the annoying part. The only way to do that, if these are independent, if they are going all crazy directions, then the only way to make them cancel is to actually have all these coefficients be 0. All these multipliers must be 0. Okay, we're going to show this once, and then I'll leave you to think about it, and we'll do lots more examples in the start of next class's lecture notes. But what does that mean for here? So just pictorially, if I take the 1, 0 vector, 1, 0, and I take the 0, 2 vector, like that, I know they're not parallel. They are clearly going different directions. So my claim is that they're linearly independent. These are linearly independent. This set together cannot be made to cancel each other out. I can't take sum of one vector and the other one and get it to crash down to 0. I can't make this happen. Mathematically, that means if I try to get them to cancel out, then let's call this alpha 1. Consider as our proof. Solving alpha 1 times 1, 0. And it doesn't have to be alphas. Let's call it A and B like normal human beings. A 1 times 0 plus B. The key thing is just 2 real numbers. B 0, 2 equals 0, 0 gives A times 1 plus B times 0 equals 0. And A times 0 plus B times 2 equals 0. That goes away, that goes away. So we have A equals 0 and B equals 0 is the only solution. So this is a slightly different flavor. It's so close to what we were doing just earlier this class, and I appreciate that it'll add confusion there. This is a different thing. I want to build the 0 vector, and I can always build the 0 vector linear combinations, but this is the only way to build it. Solution to AV1 plus BV2 equals the 0 vector. That is our test. If the only way to get it down to the 0 vector by adding these combinations is to have 0 times 1 plus 0 times the other, which is always going to equal 0. If you only can get that, what we call the trivial solution, then V1 and V2 here are linearly, and I'm going to try to emphasize this, independent. We're going to be using the word dependent and independent a lot, and so we're going to phrase it that way. All right, we'll stop there for today. I see some questions popping up in the chat, but we will definitely spend a lot more time if you take a look at the slides going forward. Independent set, dependent, independent. So we're going to focus and spend a lot of time deciphering this and practicing with it, precisely because it is such a new concept, and parts of it, until you get used to it, you do get used to it, but part of the process here can feel very counterintuitive at the start. So I'll stop there. Thank you very much, and I will check in on the chat, and also feel free to unmute if you have follow-up questions.